All right, everyone, we are back and we are about to do our Pset 6 solutions. So let's go up, or not let's go up, let's fire up Mathematica. And we are going to go to our canvas and we're going to go to our pages. We're going to go to our week 11. And then we're going to download our beam bending. And we can go ahead and open that up. And let's take a look at our problem set right here. So we have the following scenario. Let's go ahead and look at we have a beam PET. So that means we have a lane thickness. So let's go ahead and let's plug in these values here. So PET is a polymer. So let's go ahead and let's drag it a little bit over. So let's go ahead and state that our y is equal to 1 times 10 to the 9. Our L is equal to 100 times 10 to the minus 2. Our thickness, so our height is equal to, was that 10 millimeters? 10 times 10 to the minus 3, and our base is equal to 3.5 times 10 to the minus 2. I is equal to b times h cubed divided by 12, and there we go. So we have our function, and we have basically 2-point loads, and let's go ahead and start from here, 0, all the way over here. So let's do, we're going to have plus 10, actually 10 times 10 to the 3 times Dirac delta of x minus L divided by 5 minus 1 times Dirac delta of x minus 3 times L divided by 4. Excellent. So that's our function. So let's go ahead and identify some boundary conditions. So for this problem, we can see that there's no displacement at the length of the beam. So again, I'm going to assume that this is my coordinate system, x, y. This is going to be 0. This is going to be at L. So there's going to be no displacement. There's going to be no slope. So let's go ahead and plug those in. No displacement at L, no slope at L. There's going to be no moment at 0 because we're a free cantilever beam. And at L, we'll also have a moment. So we could actually calculate that moment. So if I look at my system here, I'm going to have a moment from here. I'm going to calculate it from, obviously, this because I want some of my moments to be 0 about that point. So reaction forces I could ignore. So this will move my, basically, if I look at that, that's positive. So that's going to be 1 times L over 4 minus 10 times 10 to the 3, 4 L over 5 plus my moment. And all of those must sum to be equal to 0. So I can program that in, solve that equation. So I want to solve, for example, and I want to solve 1 times L divided by 4 minus 10 times 10 to the 3 times L divided by, actually 4L divided by 5 plus M. Set equal to 0. And so that'll be my moment. We can take that, my moment, plug it in here. We have it at 0 is there. Excellent. Those are my initial conditions. Let's plug this in. We can get this. So this would be my solution. Excellent. Looks pretty good. Now we can say that my bending moment is equal to derivative of, actually, y times I times derivative of solution with respect to x2. We can look at the shear moment. Shear moment equals this times 3. And what's the problem asking us to do? So we need to determine the maximum displacement and where it occurs. So let's go ahead and we can do find maximum of my solution on the bounds where, let's go ahead and actually look up find maximum. So let's go ahead and find maximum. For some reason, it keeps trying to take me to the internet, which I don't like. I want my where's my good old internal? I'm going to copy this. I'm going to paste it into my notebook. And we're going to go here. So find maximum of my solution from 0 to the length of my beam. And let's just always just start it at 0. And we should achieve that. So that's going to be my maximum displacement of 804 meters. So again, crazy. Again, it occurs at the edge of the beam, which kind of makes sense. Will my beam yield? Justify your answer. So how can we, what is our material? Let's see. What is our material that we're working with here? Stress, I think, which is the black curve. So the black curve says that it fails at a strain of this, but we can also calculate, let's calculate stress. Why not? So stress is going to be, let's go ahead and plot our bending moment diagram. So let's plot this bending moment, and I'm going to find the maximum. Actually, I'm going to grab this there. So let's see, find maximum, actually, over here, grab that. So I'm going to find the maximum of our bending moment. And we'll see, it needs a little help, so let's see, like around 0.8. There we go. So that's our bending moment. So our stress, our maximum stress is this moment times our h/2 times, actually, let's go back and look at our minus my divided by I. So does this make sense? Let's look at our system. When we are, does it make sense that our stress is negative? So let's look back at our system. So when we push this material up, it's going to have our top should be in compression. That makes sense. That's our maximum stress. We see that that's 10 gigapascals. If we look at our yield stress or even a fracture stress, we're way above that. So it will indeed yield. We figured out the maximum stress, did that. Excellent. So now we're on to problem 2. So let's go ahead and read this problem. So let's go ahead. Oops, let's bugged out a second there. All right, let's look at another problem here. So in this problem, we have the following boundary conditions. At this point, y of 0 equals 0. Our second derivative, our moment's going to be equal to 0. Here, we're going to have at L equal to 0, our displacement, and our slope will also equal 0. So let's go ahead and let's take the same piece of code here, but now let's adapt it for this problem. So let's go over here. We are dealing with a material that is a ceramic. So that's 300 gigapascals, excuse me. A beam length of 587 times 10 to the minus 2. A thickness of 38 millimeters and a width of 48 centimeters. So we can do that. We'll also have minus 50 times Dirac delta of x minus L divided by 5 minus 1 Newton times Dirac delta of x minus 5 L over 6. So that'll be our function here. Let's set our boundary conditions. So y of 0 is going to be 0. Y prime of L will be 0. We can also have y of L equals 0. And we can also say that y double prime of 0 equals 0. Remember, that's technically y times I times that. So we've got our expression, we've got our values. Let's go ahead and let's do desolve. We get our values here. Let's plug those in. Make sure that we got all those 300. So that's our solution. We can now, let's plot this. And that looks pretty correct. So let's go ahead and we'll say find minimum of our solution. So does this look okay? About 2, yep. So I can't have the beam deflect more than 100 millimeters. Yep, we are for sure safe on that. We have our shear moment. We have our bending moment. And then let's visualize that bending moment here. And we can see our values that we get. So will the beam deflect more than should be allowed for application? No. Where are the maximum deflection required in terms of length of beam? We saw that on our previous solution here. So it will occur at 2.06 meters, and that is our maximum displacement. Excellent. Let's go here. There are several beam candidates as seen in stress strain curves below. Which materials in the stress strain curves would you select to ensure the beam does not yield? State the colors and rationale, any other concerns. So I am going to take, let's find our maximum first. 1.17, yep, that's 43. We could also find our minimum because I'm not sure which of the magnitudes would be less. So find minimum. Let's start at like 5. Okay, so we know that we'll plug in this value here for our, that's our minus m. And then let's look at here. Does this make sense? Because the beam will look like this. So the top should be in compression indeed, and that is the case. If we look at tension here, minus h over 2, it'll be this. So let's say, so we need to make sure that we're basically at 0.3 megapascals. So if we look at this, any of these will work. But just to make sure, I'm going to do orange. So there we go. Fantastic. Awesome. And then, oh, we have another one here. We're also given in C, not D, typo there. We have 3 viscoelastic materials here, blue, red, and black. Label the x-axis in terms of temperature. Determine which symbol correlates to the storage and loss modules, which material is most solid, which material is most liquid. So this is a good and open-ended question. So if I determine, if this is, let's say, T that's very, very, very low, and this is temperature that's very, very, very high, and I have 3 materials, so I know at high temperature, I need my viscous to dominate. So this would be my G my loss modulus, and then this symbol, the open symbol here for the black, would be my G prime. So basically, up to temperatures right here, I would still be behaving like a solid. So if I compare that to this one here, again, so the solids are all every solid is my G double prime. Every open is my G prime. So if I look over the crossover points here and here, it's basically solid up to this temperature, and then it changes to a liquid. So the most solid is going to be my black. My least solid, most viscous is going to be, most fluid-like is going to be my blue. Label the x-axis in terms of temperature, determine excellent. Dynamic mechanical test was done on this material as well. And this beam material is the black curve as seen below. Label the x-axis in terms of temperature and give some relative values on the x-axis. Do the same for time rate, which okay. So same kind of values here. So, ooh, nice here. We were given the values. So if I'm looking at this in terms of, we need to do time, temperature, and rate. So let's do temperature. So if this is my G prime, I know that this will be my temperature is low, and temperature is going to be high over here. The same thing for time will be low, time will be high right here. And then finally, my rate will be high here, my rate will be low here. There you go. That's your problem set 6. We are done. So we'll see you in the next video. Thanks. Bye.